Okay, so in today's video, we are going to look at Nigeria examinations from UTME, O-level to post-UTME and IDME and UPEM examination. Generally, in physics, the way examinations are given to us is based on 5 branches that we have in physics. One of them, we have mechanics, we have waves and optics, we have thermal physics, we have electricity and magnetism, and modern, or what we call atomic physics. Questions are given from these branches, so therefore it is essential to know everyone. Then one of the scariest among all of them, but the easiest, is the one we call electricity. It requires you to understand the basic concept, otherwise you think life is always difficult. But it is very simple. So in today's class, you're going to see how simple and easy we can deal with what we call electricity. The term electricity comes from the combination of 2 words. So I start physics. Then the topic, electricity. So you can see, if you circle this out, it stands clearly for city. And then if you look at here, we have electric current. So the word electric itself is coming from the word electric current. So while the word city refers to probably where you stay. So I can therefore say the word electric comes from the word electron. And electrons are also known as what? Charges. While the word current simply means flow. So hence, I can say that electricity is just a branch of physics that deals with the flow of electric current, electric or charges into the city where we stay. So the topic, electricity. The basic concept of electricity could be dated back to the time of the Greek scientists, such as a man that we call Luigi Galvani. Luigi Galvani introduced a concept called animal electricity, so we call him Luigi Galvani. And according to Luigi Galvani, he believed that electricity comes from animal. So while there was a man that we call Alexandro Volta, a town man, Alexandro Volta said no, that was wrong. Then, until later, the argument was placed and it was in favor of Luigi Galvani. So later, Volta started the full study of what we call electricity. So according to Volta, he made a simple explanation to why electrons are able to flow, why electricity occurs. So according to him, he believed that what we call electricity will only flow, or what we call electrons or charges, that they will only flow only and only if we have something that looks like this. We have a pole like this. Imagine placing an electron here. This electron that we place here cannot flow if here and here, if they are having the same potential. What do I mean by that? Look at the height of this place. Let's make here to be our point of reference. Look at the height of this and look at the height of this. So you can see clearly that here is longer than here. Then this electron here will be able to flow from this end to this end. So anything that allows this thing to move like that, we now call it a name. We call it conductor. So what about, let's look at another case. Let's say I have this region and this region to be here. Then I put an electron here to flow. You will see that there is no way for it to flow. Why? The potential energy here is also equal to potential energy here. So according to Alexandro Volta, for an electrons or charges to flow, there must be difference in the potential between the 2 terminals. So look at here. The potential energy here and here, they are not equal. But the potential energy here and here, they are equal. So there won't be any flow. So that means if I want this guy to flow, I have to bend, let's call here A and call here B. I have to make one of these two to have higher potential than the other. for the flow to occur. So if here is A and here is B, automatically there will be a flow of charges from A to B. So automatically, the major reason why there is flow is because of the difference in the potential energies between the two ends. So this end, I am going to now call it the scientific name. And what do we call that? Terminal. And here is also going to be referred to as the what? Terminal. So that means that the potential difference between the terminal here and this terminal is what makes the current to flow. So therefore, I am going to call it potential energy difference, or simply potential difference. Remember, here is energy measured in joule, here is also energy. If there is difference between these two terminals, there will be flow. And when there is flow, then work is done. You remember that work is said to be done whenever a body is moved through a certain distance. So therefore, the potential difference here is the one that is causing the work to be done. Or I simply say, potential difference can now therefore be defined according to Volta as the work that is done, as the work done in taking this unit charge. So in taking a unit charge from one terminal to the other terminal. So the container in which this is occurring is now a simple container that they call cell. You know, when you commit offense and you are kept in a small place, they call it a cell. So in this cell, the longer arm here represents the positive and the shorter represents the negative. Hence, the symbol for a cell is a long arm and a short arm that looks like this, with here plus and here minus. So what about this? A case like this where the current does not flow. It is also useful in electricity because it will enable me to store the charges. They won't flow away. So what about if I call them a name like capacitor? Then who will have been the symbol for that? The terminal A, if it's long, then terminal B must also be long too. Why? They must be of equal potential energy. So in this case, where will the current flow to? There will be no flow. And if there is no flow, the charges will be stored. Hence, this is referred to as symbol for a capacitor. Why this is referred to as symbol for a cell? With the longer arm positive and the shorter arm negative. So why in capacitor there is no difference? So remember, in physics, all our target and aim is to be able to calculate the work or energy. Remember, we define physics as a branch of science that deals with the studies of matter with respect to energy, right? So therefore, according to Alessandro Volta, the potential difference can now be defined as the work done in taking a unit of a positive charge from one terminal of a cell to another. So automatically, potential energy is equal to the work done over charge. Then, remember, we must have units, quantifier of any physical quantity. So what should be the unit of potential difference? In order to honor Alessandro Volta, in order to honor him, we now say the unit of potential difference should now be called volts. Should be called volts. Then we feel like let's honor him more. You now say, okay, that means potential difference itself can be given another name. And the name we're going to give it now is going to be voltage. So therefore, if I say voltage, I also mean potential difference, right? So that means that if I want to define a voltage now, I will have defined a voltage as the amount of work that is done in taking a unit positive charge from one terminal of a cell to the other terminal. So let's look at that mathematically. We can now say voltage, remember that's also potential difference, is equals to work or energy over the quantity of charge, right? Over charge, the work that is done in taking a unit positive charge from one terminal of the cell to another. So let's pay attention to this equation. It's very important. As I said earlier, what we love in science is what? In physics, is work or energy. Remember, they are both measured in joule. So if that is important, let's make it subject of the formula. So therefore, work is equals to cross multiply. We have VQ. So work is equals to VQ. This equation should just be noted. It's the same as the equation above. Then all of a sudden, a man came. The man, they call his name George Simeon Ohm. According to Ohm, Ohm observed that what Alexander Volta said made a lot of sense. So then Ohm now said, wow, that means if I am having something like this, case A, whereby I have A here and I have B here, electron here will actually flow. Then what about if I make it to be like this, A and B? Electrons here will flow more. What about if I make it like this, A and B? Then look at the difference between this height from the ground and this height. You can see there is potential difference. There is potential difference here. But if I put another electron here and I call here X, Y, and Z, in which case do you think that this electron will flow faster? Think about it. It will be in the case of X. Why? Because the potential difference is highest. Followed by Y, because the potential difference is a bit high too. Then it will be very slow here. Why? Because they have low potential difference. So I can start thinking. According to Ohm, Ohm now said that the flow here will only be determined by one factor. And what factor will the flow here depends on? It will depend on the potential difference. So you can see, the more the potential difference, the more the flow. The less the potential difference, the lesser the flow. The more the potential difference, the more the flow. The lesser the potential difference, the lesser the flow. So this is what we refer to as Ohm's law. According to George Simeon Ohm, if I keep certain factors constant, such as the length of the conductor that I'm using, the thickness that we call area for the conductor, and I keep the temperature of my conductor constant, these three factors are referred to as physical properties of the conductor. If the three of them are kept constant, then the current passing through these conductors will be directly proportional to the potential difference between its terminals. So this is what we call Ohm's law. So according to Ohm's law now, and from the explanation from here, you can now see that the potential difference now, or voltage, can now be equals to or proportional to the current. If proportional to the current, then the voltage can now be equals to, I will introduce a constant, and we call that constant R, which Ohm chose instead of K that you and I would have chosen. And then we have Ri. Maybe we should try to arrange alphabetically. We must have gotten something that looks like V equals to IR, and this is what we refer to as Ohm's law. So if you check this properly, you can see that without stress, we have gotten two equations that they use in electricity. One of them is work equals to VQ. How do we get that? From the definition of potential difference, right? Correct. Then the other one is V equals to IR. How do we get that V equals to IR? From Ohm's law. So if we get that from Ohm's law, we can now see that we have two equations already. But remember, we are still meant to define one thing. And that thing that we are meant to define is something that we refer to as current. Current is there with simple I, but we do not have a better idea of how we can quantify it. Let's try to imagine how somebody helped us. According to the English scientist with the name Andrew Ampere, according to Andrew Ampere, then he looked at this and he said that what about if I have a pipe like this, and I decide to start pouring tiny particles like rice, like grain here. If I start pouring them from here, how many grains will be able to move from here to here within a particular time? I would have chosen the unit of time, which is 1 second. So then I choose grain of rice. I want you to make an imagination and assumes that those rice are like charges. The charges. Imagine that charges Q. They start moving from here. They are passing through this conductor from here to here. If they are moving, if I start pointing them now and I start my time and I measure 1 second, how many of these charges will be able to move from here to here in 1 second? That is the quantity of charge that pass through a conductor in a unit time. This is the concept of Andrew Ampere. According to Andrew Ampere, the current can therefore be defined as the quantity of charge passing through a conductor in a unit what? Time. So the quantity of charge passing through a conductor in a unit time is referred to as what? Current. So hence we can now say the quantity of charge equals to current multiplied by the time taken. How do we now measure current and how do we quantify it? Then what unit should we give it? Then we need to honor ampere. So hence the unit of current is what? Ampere. So therefore, if I am able to measure certain charges within a given time, I equals to Q over time. The unit is going to be ampere. So e.g., if my current is equals to 0.3, I can write this way A. Or I can say my current equals to 0.3 ampere. So I can either I write it in full or I just write it as A. So that's how we measure current. So by paying careful attention, you have been able to derive 3 equations. One equation from definition of voltage, the other equation from just Simeon Ohm called Ohm's law, and the third one from the definition of current. That current equals to quantity of charge that is passing through a conductor in a unit time. Let us try to look at how we can harmonize these 3 equations. By being able to harmonize the 3 of them, we should be able to bring out something very interesting and sweet out of this our idea. Now, from what we have been able to show so far, you can see clearly that my voltage equals to my work or energy equals to VQ. This is coming from Alessandro Volta's definition of voltage. That voltage equals to work over charge. So I made work subject of formula and I got VQ. So I label this to be equation. Then according to just Simeon Ohm, that V equals to IR, then I label this equation to be up. Then according to Andrew Ampere, that Q equals to IC, I label this equation to be up. Looking at the 3 equations, we can now try to match them together. The most important parameter in physics is work or energy. So hence, I can now start with this equation and start substituting others in it. Work equals to VQ. What is V? IR from Ohm's law. So I can write the IR first, multiplied by Q. Does that make any sense? So therefore, I can start thinking about Q itself. Okay? Then let us start that way. Let's say from the definition of our work equals to VQ, right? So let's start by substituting Q first to get simpler equations. So if I substitute this first, let me write that here. I substitute Q first. I'm going to have V, then what is the value of Q? Then I, then T. So IT is my Q, then V is still V. So this is one of the important formulas to calculate the work done in electricity. So therefore, I label it to be 1. Easy, right? Let's look at another equation. From after we have been able to substitute Q equals to IT in this equation, then the remaining two equations will now be gotten from Ohm's law. V equals to IR. Everywhere I see V, I put IR. So work equals to, will I still write V here? No. I will write the value of V, which is I, R, I, T. You get that? I, R, that's V, then I, T before. So I, they are the same. So I can multiply them by getting I squared R, T. I divide this to the equation 2. It is very, very easy to get. So you don't need to memorize how to show them, but you just need to understand or memorize the equation itself. So one very important equation here is work equals to VIT. Work equals to VIT. They are multiplied. Multiplication is commutative in math, meaning 2 times 3 is 3 times 2. So I can say IVT, I can say VIT. Then this equation, work equals to I squared RT. That's another important and great equation. So the next equation I am going to show here is going to be the very last one. Remember, we have our work to be equals to VQ, right? Then from there we have gotten work to be equals to VIT. Remember, when we substituted IT to VQ, we got that equation. From that equation we say work equals to, instead of me to say V equals to IR now, I've shown that equation. What other thing do you think you have in this Ohm's law that is in this place? The way we learn this is that we remember this easily, that work equals to VIT or IVT. Then we now start thinking that what do we have in this formula that we also have in Ohm's law? All we want to put now is Ohm's law. Well, according to the formula, I have V in Ohm's law, so therefore I'll substitute V. Apart from V, what else do I have in Ohm's law that is in this formula? Pay attention to this I. So if I try to make this I subject of formula from Ohm's law, automatically, according to Ohm's law, V equals to IR, therefore I equals to V over what? Over R. So if this is true, if everybody can get this correctly, then I can now know that this guy is coming from Ohm's law and it can come and enter into this equation. So how do we go about that? So we have V, we multiply by what is the value of I? It is V over R. That's correct, right? Then multiply by C. So then work equals to V multiplied by V, V squared. Then times C, then over R. This is the third equation that is important whenever we are solving problem with electricity, especially when we are trying to calculate work or energy. Remember, work is energy, energy is work in this respect. So therefore, we are looking at 3 formulas. Work equals to IVT, work equals to I squared RT, work equals to V squared C over R. Say it 10 times. It will stick to your brain. After this, now, we have to quickly look at something that is very close to energy or to work. And what is close to energy or work is something that we refer to as power. Power. It's something we refer to as power. So in our next move, we look at power now. According to the equation that we have been able to show, there are just 3 numbers. 1, work or energy equals to IVT. Work or energy equals to I squared RT. Work or energy equals to V squared C over R. You can pause the video for a while and memorize this and try to write it several number of times to see if you can still remember it. Then, now that you have memorized that and you have known that, we can start thinking about what we call power now. What do we call power? To say we make an assumption that we are meant to pack 3 bags of rice. I and my roommates, and we are 4 in numbers. We are strong men, big muscles, fat and tall. We might do this job for 3 hours. Partly from the school, hostel, to the school gate. Then what about if girls were given the same task? They are tiny, they are not strong, fragile, they can easily break. For them to do this job, they might spend 2 days on it. Do you think we have done more job than they've done? No. We pack 3, they pack 3. What makes the difference? They are lazy. They don't have power. We have a lot of power. It simply means that what we refer to as power is determined by 2 factors. 1, the amount of work that you have done and the time that it takes you to do that work. If I do many work, then my power is plenty. Hence, power is proportional to the work or energy. If I spend a lot of time, my power is low. Therefore, they are inverse. Power and time, they are inverse. By merging the 2 equations, power, proportionality sign, work over 1. If I say work times 1, work. If I say 1 times time, time, numerator times numerator, denominator times denominator. So therefore, power equals to, if I introduce a constant which is 1, work over time. So power can be defined as the rate of doing work. At what rate do you do work? That's what we call power. So it simply means that if I can remember all these 3 formulas, then to get power becomes very, very easy. Why? Because power is work over time. So hence, power is equals to work over time. And power equals to what is work according to the first equation? IVT over time. So remove time. Then your power becomes IV. Correct? Let's get another formula for power according to the work. Another formula for work is I square RT divided by time. So it means power equals to I square R. So meaning that you are only removing what? You are just removing time away. So you get another important equation. So according to the third one, power equals to work over time. That is V squared T over R. Then over time means times 1 over time. So time is still cancel time. And if time chop time, then power is now equals to V squared over R. That's all. So these are the 3 important equations to calculate power whenever we talk about electricity. So you can take your time to memorize this. Then think about what you have memorized. Remove time if you are thinking about power. So if I remove time from here become work or energy equals to IV. Work equals to I square R if I remove time for power. Then for the third one, power will be equals to, if I remove time, V square over R. So these are the definition of power, mathematical wise. So these formulas will help us to solve almost all the problems that we have as far as physics, electricity is concerned. So now let's look at some of the topics proper. In this first chapter of our work, I am going to consider what we call buying and selling of electricity. So you can take a little break and join us again. Babes, yes, sir. What if one break?